All right, so pause your projects for a minute. We've got Brian here. He was a classmate of mine at Case Western Reserve. I went to school with Robin and I. So he's now an electrical engineer working down halfway to Galveston, right?
That's right.
Yeah. He's going to tell you about his career path, and the cool projects he's built, both professionally and personally. So, you know, ask him a bunch of questions and see what he has to say.
Thanks, Dave. So like Dave said, my name's Brian, and he said I currently work as an electrical engineer. I work down in Clear Lake in a company called Cyberonics, which is right next door to NASA, but completely unrelated. I'll tell you guys a little bit more about what I do there later. But just to kind of give you some background on me, you know, kind of how I became interested in engineering. Probably a similar story maybe to a lot of you. When I was younger, you know, I loved taking things apart and figuring out how stuff worked, trying to put it back together again. And I also like making things, you know, so I had all the Connects and Legos and all that stuff. So, you know, I loved trying to build something and make something new. And then as I got older, then when I was in high school, actually, like I said, I lived, Dave said, you know, we went to school at Case Western Reserve University. I lived probably about 30 minutes away from the university, and when I was in high school, I had the opportunity, I got an internship with one of the biomedical engineering professors at Case Western, so I was able to, you know, kind of help him with his research, obviously doing a lot of the basic tasks, but work on his research stuff with him during the summer while I was in high school, and the research he did there was on vision cells, and he would actually, you know, had these really high-powered special microscopes and could actually use those to insert electrodes into the cells themselves and measure their activity under different stimulus and things to try and understand how they work. And for me, that just got me hooked. I was like, this is the coolest thing, you know, that you can, you know, have the capability to use, you know, technology and engineering to understand how the body works, and then, you know, the idea is, you know, to ultimately be able to control how the body works. So, you know, his research then is feeding into technology that they're working on, trying to make implants for blind people to actually restore vision for them. And so that's what, you know, really got me started down the path of engineering. And so then after I graduated from high school, I ended up going to school at Case Western Reserve University. I actually got my bachelor's and master's degrees in biomedical engineering there. And you know, for those of you who, you know, may not or probably aren't familiar with it, biomedical engineering, you know, is kind of a broad field that encompasses a lot of different things. You know, so they kind of break it up into, you know, different aspects based on some of the engineering fields you may be more familiar with. So they have biomechanics, which incorporates biology and mechanical engineering. There's biomaterials, which incorporates biology and, you know, materials engineering. And then kind of my specialty was bioelectricity, which combines biology and electrical engineering. So, you know, the work I did there then, I had the opportunity to work in a research lab with one of the professors while I was at school there for my master's degree. And the project I worked on there was actually, you know, one of the problems that paralyzed people have is, you know, their body can't send nerve signals to, you know, anywhere below where they have a spinal cord injury. So for a lot of people, they lose control of their bladder function, that they're not able to control their bladder anymore. And so one of the projects I worked on there was actually being able to sense bladder pressure. I built a device that could sense bladder pressure and then deliver electrical stimulation in response to that, to control the bladder to, you know, prevent it from contracting when the person didn't want it to. And then they would also have a button on there that they could press to then, you know, allow themselves to go to the bathroom when they wanted to. So you know, that was the kind of thing that I was able to work on there. And then after I graduated, then well, actually, while I was still in school, I actually did an internship at the company Cyberonics, where I am now. So I spent a summer down here in Houston working at the company, and then after I graduated, I was able to get a full-time job there working as an electrical engineer. And the company Cyberonics, what they do is they build implantable nerve stimulators that are used to treat epilepsy. And so it's kind of similar to a pacemaker. There's a device that gets implanted in your chest, but whereas a pacemaker then has electrodes that attach to your heart to control your heart function, our device has electrodes that actually attach to one of the nerves in your neck, and that nerve happens to interface to a large portion of the brain, and by delivering stimulation to that nerve, for a lot of patients, it's able to either reduce or eliminate the number of seizures that they have. And so I work there as an electrical engineer. I help design we call them pulse generators. So it's a device that generates electrical pulses to stimulate the nerve. So I work in developing those pulse generators and helping to bring new technologies into those. And I can show you guys some examples of some of the different products we had and just kind of how those have progressed over time. So this is one of the devices that was designed before I started at the company. So this is what it looks like. This is what would get implanted inside your body. And then there's actually, in the plastic part here, there's a lead then that would plug into that would have the electrodes then that would get attached to the nerve in your neck. And so this is kind of what we started out with when I joined the company. And this is kind of an example of it with its shell off, so you can kind of see what the insides look like. So it's about half the device is a battery, and half of it then is the circuit board then that actually controls the stimulation. And we have then a programming system. Basically, once this is implanted in your body, we have what we call a programming wand. It's basically a giant wire coil packaged into a device that you can place over the patient's chest, and it can wirelessly then communicate with the device after it's implanted. So you can change the stimulation settings, you can change the amplitude of the stimulation or how often it stimulates. You can control all those things then after the device is implanted in the patient. And then from there, then one of the products that was just kind of being finished when I joined the company then was this model of the pulse generator. And you can see it's a lot smaller than the previous one. So with this generation, we basically combined a lot of the circuitry that's in discrete components on the other circuit board you saw. We combined it into a special chip called an ASIC, which is an application-specific integrated circuit. So it's kind of similar to a microcontroller, but it's got functions in it that are specifically designed for a particular task. So you can't really program it to do multiple different things. It's designed, with just the functions that you want to perform in there. So it allows it to be really efficient at doing one certain thing. And so by doing that, we were able to reduce the size of the device and also made it consume less power. So we shrunk the size of the circuit board on here by about half, and we were also able to shrink the size of the battery by about half. So that's how you end up with something that goes down to this size. And an example then. So this is kind of what the inside of that device looks like. So this is the battery that we use for that, and then you can see the circuit board is much smaller. This part here is actually a test connector that we use during our manufacturing process. So it allows us to access different signals on the device and make sure it's all functioning correctly before we package it up into the final device. So you guys can come take a look at those if you want after we're done. And then this is an example of one of the circuit boards for the project that I'm working on right now, which will use the bigger battery of this older device. And the reason we need that bigger battery is the thing that's added to this device versus the small one that we have is this one has the capability to communicate using radio signals. So instead of having to place a giant coil on a patient's chest in order to program the device, the physician can have, we're designing basically a tablet computer with a special wireless adapter on it, and so the doctor can be sitting, across the table from the patient, or in the case of when the device is being implanted in the operating room, they can be standing away from the operating table and be able to interrogate the device that way. And so this device basically has all the same circuitry as that previous one, plus it has a wireless communications module on here, and then we actually have an antenna that's built into the circuit board. So that's why this whole side of it looks like it's empty. There's actually, if you look at it closely, you can actually see there's a antenna actually built into the circuit board that it uses for the wireless communication for that device. So, does anybody have any questions about that stuff? Sure.
You said that they run on batteries, right?
Yes.
So in order to change those batteries when they get out, do they need to take it out?
That's correct, yeah. So that's actually a really good question. Yeah, so right now, yeah, the batteries, I would say for a typical patient, our devices last maybe about 5 or 6 years. But then after the battery dies, they have to have surgery again, basically to take the old device out and they can put a new one in. One of the kind of projects that's kind of in the research phase at our company right now is using wireless recharging to be able to power the device after it's implanted. So we're working on developing devices that, after it gets implanted in the body, the patient could have, some sort of vest or something that they would wear over the device, maybe at night or, whenever they chose to, that would be able to wirelessly recharge the battery, so they wouldn't have to have that surgery as often then to get the device replaced.
What about your nerves? Doesn't your nerves have like electricity in a sense?
It's not exactly electricity. It uses it's similar. I don't know what's the question, I guess.
So like how about you like use your nerves
to power it, you mean? Yeah, I mean the amount of energy that's in the nerve signals is very small, and it's actually it's kind of a chemical form of electricity, so it doesn't really use electrons, like a battery has that we use to power things. It uses charged molecules to transmit that energy. So it works a lot the same way, but it's not the kind of thing that you could tap into that energy and use it to power something else. Those are good questions. Yeah.
How did you get the internship with?
We actually had a program at our school that there were people there that had connections with people in industry, and they would help us find places or make connections with people then to try and set those up for us.
Is that does it still go on? Like, are those internships like still available at?
Yeah. Yeah. So the company that I'm working at now, we actually have, I think, 4 or 5 interns who are currently at Purdue University, but they're down here for the summer working at our company as well. So yeah, there are lots of companies that do that kind of thing, and I think a lot of schools have programs like that set up to help you find stuff like that. So. All right, and then the last thing I can show you guys is just kind of something outside of my professional life that engineering in my personal life it still comes in handy. This is actually a box that I built, and I used this box when I proposed to my wife. So actually the ring is inside this box, or was inside that box, and I have there's 3 cutouts in the lid on here, and I had these three gems that I had built. I actually used Google SketchUp to draw them and had them 3D printed to the specific shape that I wanted. And there's a magnet that's embedded in the bottom of each one of these, and I have sensors built into each one of these holes in here so that it can detect when you place the cutouts or when you place the gems in there. And if you guys want to come over and take a look at it, I can show you how it works. Basically, after you put all 3 gems in there, then the box will automatically unlock. So I actually set up a path through the Japanese gardens here in Houston that had flowers with these gems attached that I sent my wife walking through. As you can see right now, it's locked. You can't open it, and then as you put the gems in there, it'll detect it, and it actually lights up. I have LEDs built into the bottom there too. And they're designed, the way it works is there's a magnetic switch in there. Basically, it's got 2 pieces of metal that are really close together, and then if there's a magnet in close vicinity, you can pull those together and it'll basically complete an electrical circuit then. So then I can sense that, and the microcontroller will sense that in there. And I don't know if any of you guys are using it. I actually have an MSP 430 launch pad, is what I used inside of here to run it. Yeah, and I made them different colors. The ring I got from my wife actually has 2 sapphires and a diamond in the middle, so I put the different color LEDs in there to match that. And you can hear, I have a servo motor in there that controls the latch for it in there, and so now that all 3 gems are in there, it's unlocked, and you can open up. I put little lights on the inside, and so the ring was in the middle there. And then I can show you, I did a messy job with the wiring, but it's all kind of built into the lid there. So you can see I have my MSP 430 launch pad there that I programmed to control it, and then there's a little servo motor here, which controls the latch. I can actually reset it, and it'll be easier to see that. Yeah, so I have a little latch then that I built in there, and so I have a hook on the top side, and then there's a hook on the bottom side here as well, so when that latch goes into place, then it wraps around both of those hooks to keep you from opening it. So I don't know, that's just kind of a fun application for engineering stuff that outside of a job or anything else, you can use it to do useful stuff in your real life too. So.
That is awesome.
Yes, you did.
That is awesome.
So when do you know when the batteries are going to die?
On these guys?
No,
on this?
Yeah.
They don't last very long. Yeah, because I didn't really put too much control in there for it, so it doesn't give you any alert for it or anything, but I only needed it to really work for one day. So I wasn't too concerned about that. But
How much time did you spend on it?
I would say overall, it took me probably over the course of about 6 months working on it, but a lot of the reason it took me so long is because I could only work on it when my wife wasn't around. So it's kind of doing it in secret most of the time, so just work on it an hour or 2 here or there. So it probably took me, I would say, maybe 100 hours total, because I built the box by hand as well, so it probably took me about 100 hours to build the box and do all the programming and everything for it. This was November of 2011. Yeah.
How long did it take to make these?
So that's another good question. The actual design process, in my experience for some of these, I would say, the design itself takes maybe about 2 years to do. And then because this is a medical device that gets implanted in a patient's body, the FDA, so the Food and Drug Administration, has lots of regulations in place, with different requirements of things you have to do before they'll approve your device that you can actually use it in patients. So we have a lot of verification testing that needs to occur, which is thorough testing to document that everything in the device operates the way that we say it's supposed to operate. And then for anything that's new, new applications or anything, you have to do clinical trials then, so you implant it in a small number of patients, and monitor them closely to make sure there's no, unexpected operations or adverse effects from the device. And then after all of that, then you can submit it for approval from the FDA, and then that process itself typically takes them about 6 months to approve something like that. So it's a several year process, yeah, to do something like that. Any other questions? You guys are welcome to take a closer look at any of these if you want.
Are they really expensive?
Yeah, I mean, for most patients that need these devices, you know, their insurance
Yeah.
will cover it. But you know, I forget what it is now. I think it's you know, somewhere in between $15,000 and $20,000 for one of those devices.
Does that include the surgery?
No.
So it's like
Just that.
Yes.
Is it
Don't drop it. It's 15 G's.
Why do they have this?
So this, you know, this device basically, you know, what will ultimately get its packaged into the can is just this center part. So these outlines are kind of guides for, you know, basically cutting out the actual
So
circuit
you
board.
program it with this part.
Right,
and
so
it
we use,
comes.
exactly, we use this to program and test it, and then after it's all programmed and tested, then we basically cut the actual part out of here, and then just that center part then is what will get included in the implantable device.
Nice. Any other questions for Brian? All right. Thanks so much.
yeah.